So I have the function f of x here, and we're defining it using a polynomial expression. And what I would like to do here is take the derivative of our function, which is essentially going to make us take a derivative of this polynomial expression. And we're going to take the derivative with respect to x. So the first thing I'm going to do is let's take the derivative of both sides. So we could say the derivative with respect to x of f of x is equal to the derivative with respect to x, the derivative with respect to x of x to the fifth plus 2 plus 2x to the third minus x squared. And so the notation, just to get familiar with it, you could view this as the derivative operator. This says, look, I want to take the derivative of whatever is inside of the parentheses with respect to x. So the derivative of f with respect to x, we could use the notation that that is just f prime of x. And that is going to be equal to. Now here we can use our derivative properties. The derivative of the sum or difference of a bunch of things is just the derivative of, is equal to the sum or the difference of the derivative of each of them. So this is equal to the derivative, it's the derivative with respect to x of each of these three things. So the derivative with respect to x, actually let me just write it out like this, of that first term plus the derivative with respect to x of that second term minus the derivative with respect to x of that third term, and I'll color code it here. So here I had an x to the fifth, so I'll put the x to the fifth there. Here I had a 2x, here I had a 2x to the third, so I'll put the 2x to the third there. And here I have a x squared. I'm subtracting an x squared, so I'm subtracting the derivative with respect to x of x squared. So notice all that's happening here is I'm taking the derivative individually of each of these terms, and then I'm adding or subtracting them the same way that the terms were added or subtracted. And so what is this going to be equal to? Well, this is going to be equal to, for x to the fifth, we can just use the power rule. We can bring the 5 out front and decrement the exponent by 1. So it becomes 5x, we could say to the 5 minus 1 power, which of course is just 4. And then for this second one, we could do it in a few steps. Actually, let me just write it out here. So I could write the derivative with respect to x of 2x to the third power is the same thing. It's equal to the same, we could bring the constant out. The derivative with 2 times the derivative with respect to x of x to the third power. This is one of our derivative properties. The derivative of a constant times some expression is the same thing as the constant times the derivative of that expression. And what will the derivative with respect to x of x to the third be? Well, we would bring the 3 out front and decrement the exponent. And so this would be equal to this 2 times the 3 times x to the 3 minus 1 power, which is, of course, the second power. So this would give us 6x squared. So another way that you could have done it, I could just write a 6x squared here. So this is going to be 6x squared. And instead of going through all of this, you'll learn as you do more of these that you could have done this pretty much in your head, saying, look, I have the 3 out here as an exponent. Let me multiply the 3 times this coefficient, because that's what we ended up doing anyway. 3 times the coefficient is 6x, and then 3 minus 1 is 2. So you didn't necessarily have to do this, but it's nice to see that this comes out of the derivative properties that we talk about in other videos. And then finally, we have minus, and we use the power rule right over here. So bring the 2 out front and decrement the exponent. So it's going to be 2. It's going to be 2 times x to the 2 minus 1 power, which is just 1, which we could just write as 2x. So just like that, we have been able to figure out the derivative of f. And you might say, well, what is this thing now? Well, now we have an expression that tells us the slope of the tangent line, or you could view it as the instantaneous rate of change with respect to x for any x value. So if I were to now say f prime, let's say f prime of 2, this would tell me what is the slope of the tangent line of our function when x is equal to 2. And I do that by using this expression. So this is going to be 5 times 2 to the 4th plus 6 times 2 squared, 6 times 2 squared, minus 2 times 2, minus 2 times 2. And this is going to be equal to, let's see, 2 to the 4th power is 16. 16 times 5 is 80. So that's 80. And then this is 6 times 4, which is 24. And then we are going to subtract 4. So this is 80 plus 24 is 104, minus 4 is equal to 100. So when x is equal to 2, this curve is really steep. The slope is 100. If you were to graph the tangent line when x is equal to 2, for every positive movement in the x direction by 1, you're going to move up in the y direction by 100. So it's really steep there, and it makes sense. This is a pretty high degree, x to the 5th power, and then we're adding that to another high degree, x to the 3rd power, and then we're subtracting a lower degree. So it's what you would expect.